Hello everybody. In some of my earlier videos, I alluded to the fact that molecules are in fact three-dimensional objects that we are attempting to draw out on a two-dimensional piece of paper. And that we actually have some tools for predicting what the three-dimensional shape of a molecule is going to look like. And the simplest of those is what is known as valence shell Electron-Pair Repulsion theory. This is often abbreviated when written as VSEPR, and when people say it, they call it VSEPR, which I don't really get because it would not be like VESPR, but still, VSEPR theory. So VSEPR theory attempts to predict the three-dimensional shape of a molecule by placing the atoms as far away from one another as possible. And we've seen some of the ways that this can play out with like our linear molecules or having them on a flat plane, each being pushed out in this trigonal planar structure. And then I showed you a model of a tetrahedron when we have 4. Now, I do want to point out that here I used the word atoms. And here I've drawn out little spheres as if they would be atoms. But in fact, it's very much true that a lone pair around an atom will act similarly to an atom and change the overall geometry of the structure. And actually, we're going to see in a moment that there's going to be a little tweak that we're going to have to make when one of these is replaced by a lone pair. If we take a look at this table, we can see some of the different arrangements that are possible. So when we have two regions of high electron density, bonds or unshared pairs, then we're typically going to see something that looks like this, where the two guys here are 180 degrees away from each other, and everything is linear in shape. Here is an example of our trigonal planar, where they are all 120 degrees away from one another. 120 degrees gives us 360, which is the full circle. And this is a flat molecule, therefore. In a tetrahedron, we're going to see that each one of the angles between these bonds is actually 109.5 degrees. And again, we draw that out with using this wedged and dashed sort of thing here. Here they've given the example of methane. When we have 5 regions, this guy's pretty special compared to all the other ones. And I'll tell you why is because it's going to start off with something around the center here that looks like our trigonal planar, right? Where everything's 120 degrees apart from one another. And then it's going to place the other two above and below that, which means that these positions here are now only going to be 90 degrees. Only have 90 degrees of separation from one another. And that is going to be important as to which atoms get placed in what they call the axial positions on top or bottom, or the equatorial positions along the side. They are no longer equivalent to one another, where over here all of the positions are exactly the same. This type of structure is what they call trigonal bipyramidal. Finally, we have the case of 8 atoms, in which case we're going to wind up with this here structure where everything is 90 degrees apart. You can imagine just shoving one right into an equatorial position there and rearranging them. This actually forms an octahedron, which is another one of the platonic solids that I talked about earlier. We can draw it out in a wedge dash form like that. And here again, we now have it so that each one of these positions is equivalent to one another. So here I want to make a distinction between what we call the electron pair geometry versus the molecular geometry. So we have to consider both the atoms and the lone pairs around an atom to get its VSEPR geometry. And the electron pair geometry, when we write that out, we're going to take that all into account. So here we have carbon dioxide. We see that that's a linear molecule. Here we have ammonia, and I can draw this out, and I'll draw it out with the lone pairs where it's clear that this lone pair is pushing this into a tetrahedral sort of shape. And again, I can do that for the water molecule here. We wouldn't actually draw this bond or this bond, but I'm doing that just to kind of give you a sense of the perspective, why this winds up being a tetrahedron. Whereas in the molecular geometry, we don't draw out those lone pairs. Instead, we just assume that they are there, and that's what's giving them the shape that they have, and they tend to look a little different. So here, when we have no lone pairs around the center, the electron pair geometry is equivalent to the molecular geometry. We get linear in both cases. Whereas we would call this a tetrahedron. If I don't consider the lone pair at all, we wind up looking with something that looks kind of like a three-sided pyramid, and we call it trigonal pyramidal. And if I don't consider these lone pairs here, I no longer have a tetrahedron here. Instead, I wind up with the geometry that we call bent, where we see this bent shape in the water molecule. As I alluded to before, there is a difference in the repulsion magnitude when we have lone pairs versus atoms around our molecule. So again, here I've drawn out the oxygen water molecule, and I want to look at the different interactions. So we have lone pair to lone pair interactions. These are going to be the strongest of our interactions. We have the interaction between a lone pair and an atom. This is going to be the next strongest interaction. And then finally, we have between two bonding pairs here, and that is the weakest of the interactions that we have. So what's going to wind up happening is these two are going to repel each other more than these two, pushing everything kind of together a little bit more here. All right, and this guy's going to push on him pretty hard. He's going to push on him pretty hard. And it's going to squeeze together these two hydrogens such that we're no longer going to get that 109.5 degree angle between these hydrogens. We're going to get something more acute. We're going to get a smaller angle in here where they're kind of pushed together like that. If we take a look at this table, we can start to see what the effect of having multiple lone pairs has on the overall structure for many of our VSEPR models. So linear is pretty straightforward. We wouldn't even really need to consider anything with a lone pair there. But we could imagine if one of these guys in our trigonal planar is a lone pair and we place it here, what's going to happen? These two are going to get squeezed together, and they're going to wind up with a less than 120 degree angle between them, and we're going to call this a bent structure. We have our tetrahedron here. We've seen now if we place a lone pair here, we're going to get our trigonal pyramidal. Again, we're going to squeeze these two together, so we're going to get less than 109 because of our lone pair bonding pair repulsion here. And this effect is going to be even greater in the case of water, as we've seen, where we're going to get a value that's much, much lower than 109 degrees. And we can call this bent or angular, just like this guy here, because in the molecular structure, they both appear to be very similar to one another, even though the electronics behind it that are leading to it are different. Here again, when we have 5, we have this special condition where we have axial and equatorial, right? And when we place the lone pair, we're going to place it equatorially. Because if you think about it, if I place it here, it's always 90 degrees away from each one of its neighbors. But if I place it here, it's going to be 90 degrees away from this neighbor and 90 degrees away from this neighbor, so 2 of them. But it's going to be 120 degrees away from these other guys. So it's going to prefer the equatorial position. And this actually leads to a pretty funny looking thing where we kind of squeeze all these together, and these even start to kind of move out of plane a little bit. And we call that the sawhorse or the seesaw shape, which looks kind of silly. Maybe I'll put a GIF up for you guys so you can see what that looks like. Here we're going to have the case where we put 2 lone pairs in the equatorial positions, and we wind up with like a T-shaped here, right? So this is actually going to appear flat in its molecular structure, except for it's going to be a little less than 90 degrees between any one of these positions here, but still resembling a bit of a T. And then if we have 3 filling up all the equatorial positions, we wind up with something that appears linear. When we do the octahedron, again, all of these positions are equivalent to one another, so we don't really need to worry about that. If we put in 1 lone pair, we kind of wind up squeezing everything together, but we wind up something that looks just like a traditional, like Egyptian pyramid, like a square base with a top on it. If we place 2 of them here, we get our square planar, something that looks like a kind of like a rectangle, right? So a flat structure with 4 things binding to it. We can get a T shape if we add 3 lone pairs. But again, it won't exactly be a T because these are kind of getting squeezed together. And then, it was worth noting that in the square planar, it's interesting that everything works out such that there is no squeezing, because this guy's getting pushed on it just the same amount as this guy's getting pushed on it. There's symmetry here. So these actually wind up being 90 degrees apart perfectly. And then the same for this linear structure here. We have a certain symmetry here that actually keeps it in a perfect 180 degrees from one another.